He is currently focusing, there he is. He is an electrical engineer by training. He has a degree from Tulane and 4 master's degrees. He works for the Georgia State College, Georgia Tech. He was specializing in asking for research funds for energy, nanotechnology, electronic warfare, and cyber defense. He is with Greensleeves, and they specialize on hybrid ground source heat pump technology. Greensleeves recently won a ASHRAE Region 5 Technical Award on their GeoModule on a hybrid system for the University of Findlay. Without further ado, John Scorsone.
Hope, thanks for that kind introduction. I'm honored to do this webinar for the Corps. I think it's important for all of us to spend some time to sharpen the saw and learn about new ideas. I do invite everyone out there to subscribe to the U.S. Army Corps of Engineers Sustainability YouTube channel. There's definitely some outstanding educational videos worth watching. So before drilling into the details of the new technology that we bring and how we're lowering the cost of geothermal systems, I first wanted to start with a special thanks to everyone out there in the Corps and all of you associated with designing, building, and maintaining facilities that I have enjoyed all over the world throughout my military career. In my role as a senior leader at an Air Force base, I witnessed firsthand the challenges of taking a military construction project from concept to completion. With all the federal building mandates, I know that all of you are under intense pressure to deliver and care for facilities around the world that meets the customer needs while facing seemingly insurmountable obstacles. You deliver success despite crazy deadlines, help from others that seem unnecessary sometimes, an endless set of changing requirements and rules, constant budget pressures, the ongoing need to accomplish more with less and even less, and of course, those painful furloughs that don't seem to make any sense at all. Yet despite this chaos, you care for your customers' needs by delivering energy-efficient facilities on time and on budget. I truly respect your spirit of ingenuity, and I know it is alive and well in our engineers, architects, energy managers, contractors, and operators. You have my sincerest thanks, and you are the engine of success for this great nation. So Hope told you that I worked for Georgia Tech, and I was very happy with my time there. I had the opportunity to see some incredible new technology, everything from quantum computing to nanotechnology to cyber warfare and green buildings. My duties brought me in close contact with many businesses, but when I learned what Greensleeves had to offer, I left Georgia Tech and joined them. So let's go ahead and get started. The technology I will describe to you is focused on making the green environmental right thing to do, also the green economic right thing to do. The goal is to provide you with a new tool that helps you meet the federal building energy reduction mandates. You know, buildings account for nearly 40% of the U.S. energy consumption and greenhouse gas emissions, as well as 72% of the electricity and 55% of the natural gas usage. That's according to the EPA. Their website also tells us that geothermal heat pumps can save 30 to 60% of energy usage over a traditional HVAC system. During a new build, changing the design from traditional HVAC to geothermal is a proven means to achieve your energy efficiency targets. So the advancement that Greensleeves is providing is to provide a technology in addition that adds to the intelligent hybrid ground source heat pump system to reduce the first cost of construction and achieves the desired energy savings to ensure a system's long life. So let's go ahead and get started. Of course, any good military officer is trained to give you an overview, tell you where we're going before we get there. So I'll first talk about ground source heat pumps, so we have a common understanding of the components of a system. And I'll tell you about Greensleeves' intelligent hybrid systems, and we'll finish up with a look at some actual installations and the impressive results that have been achieved with this new technology. So let's start moving some heat. The first slide helps us understand ground source heat pump technology as compared to traditional HVAC. Traditional HVAC systems exchange heat with the outside air. During the summer, a typical building would exchange heat with a warm outside air, from a warm inside of the building to a hot outside air. This is the process of moving heat uphill. The result of moving heat from inside the building to outside the building will cool off the building to the desired set point. The higher the building demand, the hotter the outside air, then the harder the HVAC system works. Of course, in the winter, the cycle is reversed. The heat is removed from a cold outside air and you fire up a boiler and generate the needed heat. So ground source heat pumps work differently than traditional HVAC. Ground source heat pumps exchange heat with the earth instead of the outside air. The temperature of the earth is cooler than the hot outside summer air and relatively warmer than the cold outside winter air. Using water as a working fluid, heat is moved through plastic pipes in the ground. Then this heat is transferred into or out of the earth. This heat exchange process uses far less energy than heat exchanging with the outside air. There are many types of ground source heat pump systems. You can run your heat pump using closed loops in the bottom of a pond. You can use horizontal loops buried in shallow earth. That's not shown on this picture. You can also use an open loop well that extracts water at one temperature and dumps it after a heat exchange has occurred at a different temperature depending upon the season, whether you're dumping hotter or cooler water. Also shown on the slide in a light color underneath the building is something known as energy piles. These are relatively new technology. Since the vertical support columns for a building require holes to be dug, why not add loop pipe into those holes and use the earth area nearby for heat exchange? Not that the energy piles would serve your entire building need, but they certainly can lower your borehole drilling costs. However, the most common approach to ground source heat pumps for commercial buildings is the use of vertical loops, known as boreholes, that are installed nominally 100 to 500 foot deep. As mentioned in the opening slide, ground source heat pumps require much less energy to operate than a traditional HVAC system. Maintenance on ground source heat pumps is far lower than traditional HVAC systems, and the heat pump equipment will have a longer life for your overall peak electricity demand because they use far less energy compared to everyone else's compressors that are running, say, right now on the hottest day in the middle of August. Lastly, the heat rejected by a cooling dominant building can be used for water heating all year round, seasonal heating for the building, and even for snow melt in northern climates. I like to think you paid to create or move the heat, so why not recycle it and get additional energy savings? So ground source heat pumps have so many benefits, why doesn't everyone switch over to this technology? Well, the primary concern is the design of the ground source heat pump system's first cost. The number of boards you put in the ground is a major driver to the system's cost. The software used to design bore fields has been developed to account for bore field creep. Let me explain. Bore field creep is when the temperature of bore field warms up over several years when connected to a building that generates more heat during the summer than used in the winter. So a notional 40,000 square foot building that required 50 boards at 250 foot deep for year one might require 60 boards through year 7 and 70 boards to last through year 25. Additionally, we know that the energy model for a building is good for a first engineering estimate. But of course, buildings are used differently than the original design. Bore fields are upsized to accommodate potential increases in building loads. Just like your traditional HVAC system, the building demand goes up beyond the size of your system, then eventually you'll run into problems with occupant comfort or a shortened service life. The real operative question is there any way we can get all those benefits of a ground source heat pump system without all those detracting high first cost. So let me take a minute to talk about that bore field creep I mentioned earlier. Here's a typical bore field that is heating up over time for a cooling dominant building. The average temperature of the loop field rises, but stays within a safe operating limit for the indoor heat pump equipment. This is normal for a typical bore field installation. With Greensleeves and our GeoModule, we now control the average annual loop temperature back to first year high efficiency. By reducing the annual average temperature, we're able to downsize the bore field, and with a lower loop temperature, the bore field operates at a higher net energy efficiency ratio. So the bottom line here is the GeoModule using predictive intelligence to manage the bore field loop temperature to increase its overall efficiency. That's the value of intelligent predictive algorithms. But let's just look at this another way. The world is full of uncontrollable variables. The weather, the plug load, lighting that turns on and off, the number of people that go in and out of our building. Those inputs are uncontrollable, and a traditional HVAC system is just merely reactionary to what happens. As the demand is created, it responds to move heat where it needs to. You can switch to a ground source heat pump system, and now you just have a bore field in the equation that is also reactionary. You only get the amount of heat that you can put in the ground to make the system work. So all is well, provided you don't run out of additional space in the ground to store the extra heat. With the Greensleeves GeoModule, we add a brain to the system that makes decisions using intelligent algorithms to decide when and how to reject the excess heat with the use of a fluid cooler or a cooling tower. By changing the time of day or the time of year we get rid of this excess heat, we can now make predictive, optimized decisions for a thermal network. This process allows us to store the excess heat for summer and use it to make hot water or get rid of it at an optimal time in the winter. So let's take a look at what this means for efficiency. If a designer uses a traditional hybrid ground source heat pump system, it will run its cooling tower or fluid cooler when the loop field temperature gets hot. In the Nashville area, 1,000 ton-hours of fluid cooler run will cost about $25. And that's with a really good system that has an EER of energy efficiency ratio of 27. But if we store this heat and then later choose when we get rid of it in the winter, our EER can soar to 185, costing only $2.30 per 1,000 ton-hours. This is an amazing difference, and that's the value of intelligent predictive systems that control when and where you get rid of the excess heat. When we measure those loads, observe the bore field's actual performance, account for weather, we can use a predictive intelligent decision engine to decide how to get rid of this excess heat. So I hope by now I've kind of piqued your interest on the art of the possible using intelligent hybrid geothermal, reduce your construction first cost, and still achieve your targeted energy savings. So this is all interesting in theory. It's now time to move reality and look at some actual case studies with actual results. To date, we have 462,000 square feet of facilities being run with the GeoModule. This includes the Fortune 500 headquarters building, a university science center, a hospital, and offices for an engineering firm. We additionally have 1.6 million square feet on contract to provide additional projects that include 2 military bases, one at Fort Campbell and one at Fort Banning, an additional office building, 2 more universities, and in submission we have proposals to even rescue undersized bore fields that have heated up in accordance with that slide I showed you earlier. The campus setting picture you see here is our design for a community loop that ties multiple cooling dominant buildings with multiple heating dominant dormitories together and the addition of a pond loop. By creating a network of buildings, we're able to share heat between facilities, provided the run distance between the buildings are reasonable, and this is how the GeoModule is acting as essentially a thermal router. So let's start jumping into the case studies. First case study I'm going to discuss is the University of Findlay. This is a building that's 42,000 square foot, multi-story science lab addition. With all the lab space and the students, the design required a lot of airflow and a high cooling need. So with the Greensleeves intelligent geothermal solution, the University of Findlay Science Lab was designed with a 48% smaller bore field. The university has seen a 57% reduction in energy use and an estimated 35% drop in maintenance costs. The peak energy demand was reduced by 76% compared to traditional HVAC systems. That change generated an overall 51% reduction in greenhouse gases, and all of these savings are documented. The net result for the university is a $75,000, greater than $75,000 first year energy savings and an estimated $7,500 in maintenance savings. So let's look at this graphically. The blue line represents the actual energy cost of operating a traditional ASHRAE HVAC design with electric heat. The gray line is the same ASHRAE design with gas heat. We predicted the GeoModule would provide the green line level of savings. The predicted as shown by the yellow line. So a significant reduction from what we predicted. So we decided that this was so good, we needed to submit these results to the ASHRAE regional technical competition. We're pleased to announce that we won first place and will now compete with all other regions in the nation for the national ASHRAE competition. So let's move on to one more example. Here are the details of a hospital in northern Mississippi. It's a 225,000 square foot full service facility with 100 beds. If you've ever been involved in designing an HVAC system for a hospital, you know that they're energy intensive projects. So a conventional geothermal system would have been 408 bores at 300 feet. The cost of the system's installation would have been $1.4 million, and the expected energy savings would have been $110,000 per year. But with the Greensleeves GeoModule, the loop deal was designed using only 196 bores at 300 feet. When you add the cost of the GeoModule and the fluid cooler that burns off the excess heat, it came to just slightly over $1 million. But of course, the fluid cooler requires an energy usage, so the net energy savings was $106,500. A difference of about $3,500 in annual energy savings, but at a savings of over $428,000. So no one would invest $428,000 to save only $3,500 a year. That's the diminishing returns law. So with Greensleeves intelligent hybrid geothermal solution, we reduced the system's first cost. In this particular project, we made geothermal possible because they didn't have enough land space to do the full 408 bores at 300 feet. So with that, I'm here to tell you that Greensleeves GeoModule is commercially proven with installs at a hospital, a Fortune 500 university, an engineering firm. We are now on contract for projects at Fort Benning and Fort Campbell, some schools, and a museum. And now it's really over to you. What can we do for you? We'd like to help you understand whatever your project is. Do you have a 40,000 square foot building or larger where we could design a cooling dominant system that would help you make it happen? Even if we're heating dominant, we can benefit there as well. Maybe you have an existing bore field that we could extend to a second building, or if it's running warm, maybe we can help improve its efficiency. And finally, if you have a group of nearby buildings, either in place or under design, we could now share heat between buildings and take advantage of thermal energy recycling.
Thank you, John, for the presentation.
So with that,
right now we have a question from Stephanie Smith from JBLM in Washington State, and she's asking, the typical life of piping is 20 years. Do you anticipate problems with replacing energy piles at the end of their useful life since they're installed around the footing?
Okay, well, I take a little exception to the question. I think pipe traditionally is warranted for 50 years and expected to last 200. And don't take my word on it. Go out to an IXPO website and check that. The typical geothermal systems, the heat pumps themselves, last on the order of 20 to 25 years. And I would say better managed loop temperature, the life of those heat pumps can be extended because they're operating basically in a happier temperature range for them. The more that you operate them at the higher end, the lower the life you're going to see out of your heat pumps.
So good, we've got a few more questions. And just to remind people, if you want to ask a question, you can either email the question to myself, or there's a Q&A box, which is right under the webcam where John's located, and you can type it in, and then I can read it out so that we have a copy of it on the recording. All right, so the next question, are the bore fields spaced differently when using this type of system?
No, the bore fields are typically about 20 foot on center. We don't adjust bore field spacing. We use traditional spacing of the bore field. Our company is quite capable of being the designer of record on a bore field, and we're happy to partner and advise others. The important thing, and let me add, net land area used is smaller because obviously if you're putting in fewer bores, your now land area that you impact is a lot smaller.
All right. Next question. How would designers design around the GeoModule? Is there a specific software? Do you have published design guides? What other kind of resources are available for the AE portion to work with your systems?
Certainly, it is the company's long-term goal to take our simulation tool that designs up to the GeoModule and make it publicly available for all engineers, either as an add-on to GLD or something in Autodesk. We're not there yet as a company to make it publicly available and for everyone, but that is in the long-term goal. If someone has a specific project in mind, we're more than happy to walk them through the possible savings on their project. In general, we're seeing a 30 to 50% reduction in bore field size for cooling dominant applications.
Great. Next question is from Adriana Kenakur at DPW Fort Hood. She's asking if you could readdress in your discussion how you reduced almost in half the bore size.
So remember earlier in the discussion, I said bore field, the traditional ground loop design software or other softwares that you can get, you can do a 1-year design, a 7-year design, a 25-year design. Well, those additional bores that you're putting in to make it last the 25 years aren't providing you any more capability. They're just allowing for more heat to be put in the ground over time than you take out. And that bore field is heating up. So the software accounts for this. Well, with our design, there's no need to have the bore field heat up over time because we're managing it back to first year performance. And when you manage it back to first year performance, all that excess spare capacity that you put in becomes unnecessary. So we're not changing the physics of the ground. We're not changing the performance of the loop pipe. Instead, we're managing over a season how much heat is held at any one time in that, essentially, the thermal battery in the ground. We're not letting it get overcharged.
All right, and Alan Turpoli is asking for you to define your use of the word hybrid in the context of the presentation.
So a hybrid geothermal system, a traditional geothermal system is just loop fill. There's no cooling tower or boiler connected. A hybrid system is a geothermal system that you can hybrid on the cooling side by adding a fluid cooler or cooling tower, or you can hybrid on the heating side by adding some kind of boiler. You can actually hybrid on both ends if you need to. That's a little bit of an expensive way to go, but it's been done. And of course, the intelligent hybrid
Linda
is
Fowl
the one
is asking, and this is kind of a contracting question, would Greensleeves GeoModule, because of the kind of specificity that you've discussed, would it be considered sole source? And really kind of, I mean, you have experience obviously with the government, so maybe you're fine answering the question, but I mean, or overall we're kind of asking, like, who are your competitors, and is that something that we would have a contracting issue with?
Yeah, so the hybrid and intelligent hybrid has been out there. Hope I've sent you papers before that others have done this technology. So it does not enter anyone into an exclusive arrangement with Greensleeves. Of course, I will tell you we're the absolute best in the world, and no one can compare to what we have in the way of patent-pending algorithms. But certainly intelligent hybrid or hybrid systems can be done by others. It's just that we think we're out in front and we're the best. And I'll offer to everyone else out there, if you have a specific project in mind, we can forward you Corps of Engineers approved specs, control specs that have been used, contracting specs that allow a contractor to come forward with cost savings innovations, whereby they have to prove the cost savings doesn't stick you with a large energy bill on the back end, and we achieve both. We save you money, and we save you on the first cost and save you money on the energy bill on the back end.
Great. Second part, there's another question, also from Alan. He's asking, is it better to use individual cool water source heat pumps inside the building, like a hydronic system? Or is it better to connect the ground source to a conventional VAV, variable air volume, HVAC system?
I think the answer is going to be situation dependent, but on this one, I'm going to use a lifeline. Steve, if you're on and you can come up, I'm going to ask to see if you have an answer on that one. Oh, he's not on? Okay. If you will pass me Alan's contact info, or Alan, if you get a hold of me at my email address below, I'll get you a very specific answer. I want to make sure I've got it in the right context and not misquote what's possible with the technology.
All right, we have another question on the different styles. You mentioned the 3 different systems. You had the vertical, you had the pile, and you had the horizontal fields. Do you have any projects that you're currently working on that are utilizing the horizontal ground source field?
No, we don't. And I will say that in general, while we can integrate with that and you understand how it's behaving and adjust our system to account for its actual performance, I would say in general we're not a very big advocate of the horizontal level. And the main reason for that is because horizontal is so close to the surface of the earth, it's more reactionary than the deeper earth vertical bores, but certainly less reactionary than outside air systems. In home applications, they're pretty popular, especially up in the Northeast. So we can integrate with that. I don't think we have any current projects where we have.
Another question from Alan. Would the use of the geothermal systems vary much from Fort Gordon, Georgia to Fort Stewart, Georgia, just based on that climate? And I will say that that's kind of a borderline in the ASHRAE climate zone, so that's kind of a tricky question.
Sure. So let me just offer to you that every application depends on 3 primary things. You're always going to start out with the physics of the situation. and that is the energy model. Piece of critical information that you need is the thermal conductivity of the ground that you're on top of. So if Fort Gordon's thermal conductivity is different from Fort Stewart thermal conductivity, it will have some effect on the number of boards. All of this is accounted for in GLD. And by the way, our designs start off with the GLD full-size bore field, and then we run through some simulations to determine how low can you go and safely manage the bore field and still achieve the energy savings target. And of course, the last piece of information is the ASHRAE weather. All of those go into the equation in the decision-making engine.
All right, we have a question. At what point, since you're familiar with kind of the military process, does geothermal need to be considered, or ground source heat pumps need to be considered within the project development? Is that something that is identified early on at the planning phase, or is that something that you can kind of add on once you've already determined
You
where
certainly
the site
can add it on later, but I would argue that the earliest in the process that you take a look at the energy savings possibilities for ground source heat pump, the better you're positioned to succeed. If you are 100% design complete and ready to go out for a design bid build, that's probably not the time to add a ground source heat pump. But if you're in the process of submitting your NILCON justification paperwork, that's the time to take a look at what the art of the possible is. Certainly, if you've already added ground source heat pumps as part of your design, you can be as late as 90 or 100% design, and provided that you're open to changes that will save you money, we could actually come in even that late and tell you straight up whether or not it makes sense for you to save money and implement this technology. Again, it's about achieving life cycle cost savings for you. If it doesn't achieve life cycle cost savings for you, we're not going to force a not good idea on a project.
And this is a question that can either be for John or for Hope or both of you guys, but kind of with your familiarity of the standard Army facility types that we have, DFACs, temps, barracks, things of that nature, are there particular uses, functions, or facility types that lend more towards a ground source heat pump system or make them more efficient?
Let me jump in here.
Or is it kind of negligible?
A cooling dominant building is an outstanding opportunity. That would lend towards it. The dining facility is outstanding because if you integrate the use of the ground source heat pump to provide for your hot water, you know, even a gym type facility would be outstanding. Now, the amount of savings you can achieve is dependent upon the energy cost in your region, the cost of drilling in your region, the thermal conductivity, the overall energy model associated with your building. All of these factors go into the mix. But if you go on the IGSFR website, you can see ground source heat pump solutions have been done all over the United States. And even the United States is behind the adoption rate that's been achieved in Sweden.
And Hope, did you want to add anything on there about facility types that you've already been working with that have utilized ground source heat pump technologies, just as a reference for some of the guests?
Yes, you know, and as John said, what we have found is that facility types that have a mix of heating and cooling, or buildings that are either heating dominant or cooling dominant that share a combined well field are actually excellent candidates for geothermal. You know, we have used geothermal well fields for a dining facility, for offices. You know, what I would encourage anyone to do is that, you know, at the very beginning of the design phase, perform an energy analysis and find out what is the energy savings potential of, ground source heat pumps versus other HVAC system types.
John, do you want to talk at all? We had a question about what is the kind of operations and maintenance of the
right. So
technology,
the nice thing about the system
how does that kind of
is
switch over with DPW as far as what they're currently doing to operate and
what to
maintain?
do. It's self-learning. It knows what to do next year based upon how it performed this year. And there really is no required preventative maintenance of the GeoModule. It's like you bought a laptop with some software, and it works as long as you continue to operate within the current set of parameters. Now, if you decide to go add another building or add more boards or drastically change the system, naturally you're going to need a little tune-up that goes with your redesign. But the system itself operates, it does not require an external connection to anyone else. It's totally self-contained, and once it's commissioned and left up and running. It can send you reports through the building energy management system on how it's doing and what kind of energy savings you're achieving. So those are the issues. So there is no recurring hook back to you or an ongoing software service agreement. Certainly we're willing to enter into those if someone would like a health checkup year after year. There's no hard requirement, or there's no, if you will, golden handcuffs back to us forever.
All right, and we have another question on what size facility is needed to start considering a ground source heat pump. I mean, obviously, like maybe a single family home or some sort of a training center that doesn't have the HVAC isn't appropriate, but at what point does it become efficient or cost effective?
There's a webinar that was done by the U.S. Army Corps of Engineers. An individual who's a member of the Corps put in, I think, 2 or 3 wells in his backyard to provide for half of his home's heating and cooling need. So you can go as small as you need to, and you can go extremely large. The Corps of Engineers project for Fort Benning, I think, is 600 or 700 boards at many hundreds of feet deep. So it can go all the way in. For our technology, because we want to work on the bigger projects until we get greater market adaptation, we're seeking a 40,000 square foot or larger facility to kind of make the economics of it work better. We could work on something smaller, provided it was, say, at least 100 tons of heating, cooling need, or cooling need.
All right, and another question really quick is, are you in general agreement with the report by ASHRAE that's titled The Optimization of Cooling Dominated Hybrid Ground Coupled Heat Pump Systems? Basically the report states that ground source heat exchange in a cooling dominated hybrid system should be sized only to meet the peak load. Do you have any comments or statements on that?
Heat rejection required. I mean, remember, if you size it for a peak load on a hybrid, what the typical hybrid is doing is you have so much capacity in the ground, and when that ground gets too hot, you now use the hybrid in the summer to get rid of a little extra heat. But remember, that's going to occur at the worst time of the year to operate that cooling dominant system. What we want to do is manage that loop temperature lower and operate the hybrid at off-season. It might be slightly bigger than a traditional hybrid that you would use in summer, because we want to pump as much volume of heat through that device at the lowest energy savings possible cost point in the winter. So the exact sizing is a function of the specifics of your facility and what you're trying to achieve. But we are in like agreement that the focus is to get the overall system cost down as low as possible on first cost and down as low as possible on life cycle energy costs.
I promise we won't get too political and make you comment on everything that ASHRAE does. All right, so just a few more questions before we have to kind of cut it off. But we do have a question: is it feasible to use a community well field when coupled to a DFAC, a dining facility, and 3 barracks training facilities? So you've got 4 facilities total, a dining facility,
DFAC would also have
and then 3 barracks facilities. And then if you could repeat why a DFAC can use ground source.
Stuff like that, as well as those dormitories would have a need for hot water. So the exact amount of bores and the size of the hybrid device would totally depend upon the energy model of all of those buildings, the location, meaning the weather data, and the thermal conductivity. But to get into the details of how exactly we would do that, I would invite whoever's asking that question to get a hold of me and we can get you specifics on your project. The last piece of information I would put on there is ultimately this system is sharing water in a loop. Remember, we're talking about closed water, water in a closed loop moving around to reject heat. If those distances between those buildings get excessive, you're going to pay a large penalty to pump that water around the loop. So we want to keep, square blocks sized projects, not miles apart projects. So you want to keep that pumping energy as low as possible. Again, we're about trying to achieve the lowest possible life cycle cost, and we wouldn't implement a solution like that just because we could. We would implement it because it would save you money.
All right, I lied when I said we weren't going to get political. If you had to comment on whether ground source heat pumps were renewable energy, what would you say, knowing that we have some federal agencies like the DOE that have said that since it doesn't generate energy, it's not renewable energy, it's just a highly efficient system.
Is a renewable source. Now, since you're not actually generating electricity, if that's your requirement to be a renewable energy, that there's a generation of electricity, then no, we do not meet that standard. But if your definition of whether or not it's a renewable energy is a function of where it comes from, truly the surface of the earth sees its heat and its temperature as a function of the sun, which I think most people would agree is a renewable energy. What I can say is I will put up ground source heat pump economics against the economics of most any solar or wind project. Earlier in the program, remember I said we wanted to do the green environmental thing as the green economic thing. And if we aren't saving you life cycle cost, if we aren't helping you meet your 30% better than ASHRAE 2007 and making it economical for you to do so, and we want to look to the next project, but we're convinced that we can help you.
I think that's a good answer, and it's a good perspective to look at both where the energy comes from, but also what the energy is generating. So it's pretty good food for thought. I think that wraps it up for questions. I appreciate you doing the presentation, John, and we'll have your webinar loaded on the website by the end of the week. Before we cut off, I'd like to open it up to Hope to talk a little bit about the Regional Technical Center of Expertise for Geothermal Energy Technologies and Ground Source Heat Pumps. Hope, I guess I was hoping that you could just outline what types of work that you've been doing and what services you offer and how they can get a hold of you. But thank you, John.
Hi. Yes. Okay. John and Lindsay, thanks so much. John, you've done an outstanding job, and we really appreciate you presenting today. As Lindsay said, we do have a ground source heat pump, REX, and what this is, it's a collection of individuals across USACE who specialize in ground source heat pumps and wellfield design. We are a group of individuals who are mechanical engineers, electrical engineers, geologists, geotechnical engineers. We even have cost engineers on our staff, and we've worked on a variety of geothermal projects. Our group has several reviews underway, and we have two ground source heat pump projects. One of them is in construction right now at Fort Campbell, and the other one is in design. So we've got some very exciting things going on, and if you have any questions about ground source heat pumps, or if you would like help with your project, please either shoot myself or Lindsay an email. And with that, Lindsay, I will turn it back over to you.
Thanks, Hope. And I just want to reiterate, so Hope's group are all core employees. So sometimes they can get their assistance on your project funded through central funding. So if you do have any questions or comments or just some insight, or if you're looking for training opportunities, the RECX for ground source heat pumps is a really great resource. Thanks again, John, and I will have this posted. Again, we have a new quiz for the next round of 5 webinars, so you can get your 5 PDHs. So that will mean that there is an opportunity to get 10 total. We had a quiz for May and June. This quiz is for July and beginning of August, and then shortly I'll release the 3rd quiz. Again, if you have any questions or comments, please send us an email. Thank you guys for your time.